it's continuous, differentiability is a stronger condition. So I can't use that, which really annoys me. But I'm going there, all the way down. So last time I told you that starting with first principles, geometry, bringing you back to math classes when you're a kid, I'm going to show that for theta small enough, sine squared theta is less than or equal to theta. You can see it from the graph. I wanted so badly to go in and say mean value theorem, but wait a minute, that requires differentiability. Can't do that. Taylor series, well, I can't do that either because that requires differentiability. So once you have differentiability, all of what I say is a lot easier to see. But I'm trying to show it's continuous, which is a weaker condition. So the first thing I showed you is I take the unit circle, which I love the unit circle. In fact, we used it in class here. I used it in class for the one that used Lagrange multipliers. I used the unit circle that sine squared plus cosine squared is equal to 1. It's the first parametric plot that you ever did. It's a parametric plot. You have x is equal to sine t, x is equal to cosine t, y is equal to sine t, and you plot those dots and you get the unit circle. It's got beautiful properties. You can actually do this with your children when you finally have children. You can have them measure across a circle with a measuring tape, measure around the circle with a measuring tape, plug it into Excel and take the ratio. You'll get pi, something close to pi, so you can teach your kids about pi with just measuring pies. So there's good things about lots of goodness in the unit circle. So if you use the properties of geometry and take a sector like this, theta, you know that, and you drop down here, you know that sine of theta is opposite over hypotenuse, which turns out to be 1. And then I also talked about this sector, shaded area over here, which we can see is larger than this, than the area of the triangle. So the sector's area is going to be the fraction of the circle that is represented here, which is going to be the whole thing. The fraction is theta divided by 2 pi times the whole thing around. This is the fraction. This fraction of the circle represented by wedge. The what is called sector times the area of the whole circle, which is pi, and that's theta over 2. So now I have that sine theta, the area of the triangle. I didn't actually need this, but area of the triangle. So that this opposite area here, I did need that. It has length opposite, what I call opposite. So the area of the triangle is equal to 1/2 base. I'm just going to put base there for now. What do I have here? Make sense of this. I should have written neater. Yeah. I don't want that though. I don't have what I want. Yeah, because the area of the triangle is 1/2 base times height. So I get a 1/2 here. Oh no, I don't think here. I somehow wanted to replace this with a 1. Oh, I know why I did that. I know what I did. My writing's messy. I can also drop down this guy here, and then I have this triangle over here as well. This shaded triangle without the sector. The sector is this piece right here. The shaded triangle has base 1/2, base 1, and the opposite, the height, is going to be sine theta. So let me draw this picture better. Note to all of you, make sure your notes are very clean so that you can read them, because you have better memories than me. So here's this length here is sine theta. And then you have this triangle out here, and then you have the sector, like this. So the sector's length, the sector's area is going to be theta divided by 2. That's a sector area, which I just talked about up there. This triangle's area, this triangle here, that's before the sector, has base 1 and height sine theta. That's where this thing comes from. And then area of the triangle is less than the area of sector. And then I get sine theta divided by 2 is less than theta divided by 2, which implies sine theta is less than theta. Following? Ask me questions if you're not tracking.
Why is it the equal possibility?
It doesn't, you have to put, unless like 4 equals. So you can take that out if you want to.
Didn't you say we were trying to show sine squared or something?
No, sine theta is less than theta. I need that. All right, the reason I need that is I need to take the x squared out of the sine because I need x minus c, right, eventually. So to take that x squared out of the sine to do my proof, I need somehow a way to separate the sine theta from what's inside the sine of x squared from what's inside, which is the x squared. So I need this inequality to pull the argument out. Oh, no, sine. Sine. Good?
What if you have the area of the sector is theta over 2 pi?
Yes, that came from, this is the fraction of the circle represented by the sector. This is the area of the whole circle. You multiply those out and get theta over 2. Kelly? So this is the triangle.
Is there a limitation on theta?
Yes. Theta's got to be small enough for this to be true, right?
Let's do less than.
The unit circle. So x squared plus y squared has to be less or equal to 1 for this to be true. But theta close enough to 0 works, right? All right, now some more stuff. So you believe this? If theta is small enough now, I get this. All right, so you can actually go through each quadrant. I just did the first quadrant, like all high school teachers do. We just work on the first quadrant. But you can repeat this for the second quadrant, the third quadrant, same kind of argument all the way through. You can make triangles. And what you'll do is repeat analogous argument yields minus theta is less or equal to sine theta. It's less or equal to theta. You'll get negatives, and you'll get around, as you go around the circle, some of the signs will change. So this is what's going to give you the whole thing, that the absolute value of sine theta is going to be less than theta. Good? High school geometry, that is a trig proof. I don't think we ever got something like this in trig, but I remember them talking about sectors. All right, so I got that. How am I going to use that? Well, let me go back to what I'm trying to show. I'm trying to show that epsilon is greater than 0 given. There exists a delta greater than 0, such that the absolute value of sine of x squared minus sine of c squared is less than epsilon when x minus c is less than delta. So what led me to this path that I took? If you remember your scratch work, we're definitely going to ask one of those as one of the 5. Like, how do you show something continuous at a point? How do you do that? You actually go backwards and do scratch work, and then get x minus t isolated somehow after you choose your epsilon. And that delta might be a function of epsilon, and your algebra might be yucky and messy, but you really need somehow to find this, there exists this delta. That's what you're after. So why I did the calculations I did is because I need this x minus t isolated in my scratch work. And right now, if I give my epsilon and I start here, I can't take the x out. So I looked at this and said, I wish the sign wasn't there. Like many pre-calculus students say, I wish the sign wasn't there. So how do I get it out of the sign itself? Well, I can't get it out because there's no algebra equation that'll take it out. So I needed something that will give me an inequality to move it out so I can get to some scratch work. So that was the logic behind this.
So what exactly are we proving now?
We're trying to prove the continuity of sine of x squared. Okay, so next, I have another problem. The other problem is I need to somehow get this x squared and c squared out of there at the same time. So I need to somehow move the x squared and c squared together in the argument. And so I looked up trig identities. I actually went down this rabbit hole looking up stuff as I'm going, like, how do I show that sine of x is less than x inside the unit circle? So I went there, did the geometry, and then I went and like, I need this argument to be inside one sign, not separated. Trig identities. So I looked up trig identities, and there's an obscure one that says, because I don't remember it, these are the ones that you get in when you're integrating. They probably make you prove it as a pre-calc student, maybe. It's usually the bloodbath time of pre-calc. You start asking these questions. I just looked up one. I just went on Google and said, what is the sine? How do I get sine of alpha minus a sine of an angle minus sine of another angle? Look for a trig identity that does that. And this is the trig identity that does that. So I confound this guy by 1, and now I've got the arguments inside 1 together. That's what I wanted. Not inequalities, for trig identities. I say obscure because I remember from calculus, you remember the double angle ones because you have to take stuff out for u substitutions. You remember one for cosine squared. Those are the ones that you use more often. I don't remember using this. I remember it in the back of the pre-calc book when I taught it. But I don't remember ever really using this.
tech for that is really fun.
What?
Writing out the tech for that is really fun.
With alphas and betas.
Yeah, sine, alpha, beta, frac.
Okay, I'm ready to go. By the way, I thought I was going to get your lecture notes done in time to watch the Rangers game. And I was really worried at this point. Like, I'm going down these rabbit holes and I might not make it. And then I remember we cut cable anyways. So didn't get to watch the Ranger game. So this is what I wanted to do. This is what my mind was thinking. That's what I wanted to do. So that I can get the x squared and c squared all together inside one argument. And now I think I'm good to go. Because now I can do this. Now it looks more like the ugliness that you had in your problems where you now can set your delta, right? I set my delta to be less than, this is my scratch work, by the way, this is not a clean proof. Even when it's a clean proof, it's not gonna look clean, it's gonna look awful. So this is my scratch work, trying to find delta. Set x minus c less than delta. So you've seen me do this before. X minus c is less than delta, bigger than minus delta, which implies x is minus delta minus c, delta plus c. And I really can take the right-hand one. So I'll take x is less than delta plus c, implies x plus c less than delta c. C on the right side.
Ma'am, how did we go from that up there to
Good.
like
Create identity from here.
right?
And then from here, I use the fact that x squared minus, if the argument is close, if x squared minus c is close enough, I can drop this, take it out.
Oh, because it's less than
That's the,
sine.
yes, sine beta less than beta. And I haven't put all my epsilons in there yet. I'm just thinking about the scratch work that's going to get me the delta. So all of this is just scratch work.
Is that two times one now?
Yes, because I got a 2 from the trig identity. And the 1/2 comes from the, yes, so they cancel.
We should do the question of x squared plus c squared.
Oh, it's less than or equal to 1? Yeah. It's terrible. Unless you like pre-calc. I have to give you guys that problem my daughter gave me. Find the polar moments of inertia for the area bounded by 3 hyperbolas. She came in and said, Mama, can you help me with this? Like, I can, but I don't want to. I don't want to help you with it. You're on your own. All right, tracking? I'm going to put it all together in a second. This is all just nasty scratch work, just showing you where I got everything from. I'm about to set my delta in a second. Yes, because I have x is less than delta plus c. So x plus c is going to be less than delta plus c plus another c because I have another c in it. All right, I'm ready to go. Now we're at 2:30 in the afternoon on a Sunday. The Rangers game started at 3. I'm like, I don't know where this is going to go. I might not be able to watch.
I've talked for it a little bit, so.
Yes. So what do I want? I want my sine of x squared minus sine of c squared to be less than epsilon if my delta is the right choice. So I want to solve for delta so that this upper bound that I just got from messing around with the signs is smaller than delta epsilon. That allows me to solve for the delta. Right? I want to start here with x minus c less than delta and end up. That's what I want. So I guess this is free calc, quadratic formula to solve for my delta. And that's when I said, I'm going to Mathematica. So there's a command on Mathematica called reduce, and it'll solve an inequality for you. Right there. Well, the sure. So again?
Like on the.
Yeah, I don't think I'm going to make you guys do this.
I'm just taking notes.
Okay, so I asked Mathematica to solve this equation for me. That's how you solve a quadratic inequality. Set the less than to equal to 0 and look what the cusp of the boundary is. And it turns out that delta is equal to minus c plus or minus the square root of c squared plus epsilon divided by 2. No, plus 4 epsilon. Yeah, I think I actually used quadratic formula. I didn't go to Mathematica. The North Dakota Mathematica used the quadratic formula. Sorry for anybody who's from North Dakota. And now I have a delta. Go ahead. So right here, if I set x minus c less than delta, I get this. I can solve for x. I really care about this part of it. So if I have x plus c without the absolute value, take off the absolute value, it's bounded above by delta plus c. That's it, x plus c bound. And then I have an extra c. So it should become delta plus 2c. Yes, it should. So I have the 2c in my notes actually. Yeah. So this is what you get. That is right. Right. I was gonna ask for the 2. 2's get lost. I told the ODE class 2 is equal to 1. We do it all the time in real analysis. 5 is equal to 1 too. All right, I simplified this guy up, and I get this thing turns out to be minus c plus or minus the square root of c squared plus epsilon. After you do all the cancellations, it's fine. All right, we're almost there. The important thing to realize here that you're seeing is delta is a function of epsilon. I literally can see that. That's the important takeaway, that my delta is actually a function of epsilon. And you've done this in class with Excel, where you actually see, like, you choose an epsilon, the delta changes. So I can actually see that in formula point of view. All right. If I set delta So what do I want? I want two things to slide. I want x to slide over close enough to c so that x squared minus c squared is within the unit circle. And I also want my delta to be smaller than this. Just take the minimum of those two guys. So I will slide down my x to c close enough so that I get both of those things to happen. Then then we know this is true because I invented it in such a way so this is true. So then when this is true, then I have this, which is less than to this, because I'm split my x down so close enough so that I'm within the unit circle, which is this when I factor it, which is less than this by an upper bound, which was less than epsilon. So
Isn't x minus, like, shouldn't it be less than just delta squared plus 2 delta c? Why is there an extra?
oh, there shouldn't be, it should be exactly what I had up here. Delta is not squared. Right, it's that thing over there.
Okay, so then it should also be 2c, not 2 delta c, right?
2c, yes. I think I multiplied the delta in and yeah. Lots of algebra. Lots of, it's like pre-calc. Yeah, I was really happy when mathematics was invented. I can get my PhD in math now. All right, so a couple things to notice here. Number one, the only thing I think we left out of pre-calc is conic sections. I was trying to figure out a way to bring it in, but we left that out. But this is like a trip down into pre-calc. The math is messy. The front proof is inelegant. It's not a nice proof. And I could have just used that the composition of two functions that are continuous is continuous. But I already started down this rabbit hole. But what I wanted you to see from this is that my delta is actually a function of epsilon. Where's my epsilon here? Yeah, the delta I chose in the end had epsilon in it. Does that mean it's not uniformly continuous by this? Does this tell me that it's not, because my delta is a function of epsilon, does that tell me that it's not uniformly continuous? Because uniformly continuous, as you wrote on the board the other day, requires not to have epsilon, there to be dependent on epsilon. So does this satisfy that? Say, well, it's not uniformly continuous because my delta was a function of epsilon?
No, because uniformly continuous is like, it's only a function of epsilon. We haven't proven enough to say that. Like, because delta is a function of epsilon, it doesn't necessarily imply it's not also a function of position on the line.
A little bit closer, it's that maybe I just was really bad in my choices and I ended up with a delta that's a function of epsilon, and there's another delta somewhere out there that would work for them all. I just haven't found it. Right? So what would you like me to show, that wedge is actually had an area bigger than the triangle that I had?
So,
I don't want to go that far.
Because we showed that delta is a function of epsilon, we know it's not uniform.
Not necessarily, right? So that's what I was just asking you. Do I know that for sure? And the problem is, I could have just chosen badly for my delta. It seemed bad and a bad experience. So it could have just been that I had just a bad choice of delta that was dependent on epsilon, but there was a superior delta that worked for all the epsilons. So it could be that it's my choice. So this proof doesn't guarantee that it's not uniformly continuous. It only guarantees that it's continuous, right? So I have to go and try to show it's not going to be uniformly continuous. When I show that for you, that one's out. So it's not bad like this.